Hello, welcome to Lesson 16 of Water Systems Design. The lesson's titled Storm Sewers, Inlets, and Conduits. The lesson is mostly on inlets, inlet hydraulics. We'll discuss storm sewers, and this is segueing into conduits, which is the subject of Lesson 17. Quick review, if we look at this flow that's going into this corrugated pipe, we actually have all three flow regimes manifest here. Location A, which is the blue dashed line, the flow is most likely subcritical, but it's starting to accelerate to make it into the inlet or into the pipe. At location C, the red line, rough guess of where critical depth is occurring. And location B, we have just passed under critical depth, we're supercritical, and it's likely headed on towards a jump somewhere downstream, not in the figure. So all three flow regimes can actually occur quite physically close to one another. So the outline of this lesson is inlet designs. Inlets into storm sewer systems are actually fairly complicated hydraulic structures, and so most of the design methods are based either on experiments that were conducted by the Federal Highway Administration or various other similar type agencies, typically in support of transportation infrastructure and or municipal engineering. These are going to be representative of the typical design computations involved, but they would be adjusted to fit whatever jurisdiction you're performing design in. So storm sewer systems are comprised of inlets, which capture the runoff from the surface and convey it into the storm drainage network. The conduits themselves are used to collect all that storm water and ultimately transport it to the outfall. We use lift stations if gravity flow alone can't accomplish the task, and detention and diversions are an important component of the system. Ultimately, the outfall releases water back into the environment so that we have places to kayak, as pictured here. So this diagram is a diagram of a storm sewer system, kind of comprising all the various parts. Not necessarily realistic, but it'll give you a guideline on what comprises a storm sewer system. Up here where the cursor is making a circle and hopefully making you nauseous, we have a parking lot, and it's going to drain into some inlets. We have a roadway, and we have curb and gutter inlets here. And these green objects represent the inlets. Then there's the conduits, which are the blue lines that have just materialized. The conduits join one another in junctions, which are shown with this magenta kind of color. In this diagram, they're shown as manholes. And there's a detention basin over here to help control the outflow and store water temporarily. There's diversion structures which allow certain fractions of water to pass through a treatment system, whereas other fractions can pass beyond it. This is a hypothetical lift station. Here's the outfalls, and that completes the storm drain system. So when we talk about inlets, we're talking about these objects that are pictured here in this photograph. So this photograph is a grade inlet. Looks like it's on a curb side of a motorway, and the water's coming this way into the grate. This distance here, which is called the red line, it's not called the red line. The red line is indicating a spread width of the water flowing towards the inlet. Here's the actual inlet, and then if there were flow to pass beyond this inlet, going in the direction that the cursor is moving, that would be called carryover. There's no carryover in this particular photograph. All the water that's carried by this curb actually gets to the inlet and actually gets a little extra bonus water here for water that's coming out of that subsurface system. So a storm drain itself is a system of curbs, gutters, inlets, pipe networks, open ditches, buried ditches, that receive runoff and convey it to some point where it's discharged into a pond, channel, stream, or another pipe system, and ultimately onto an outfall. The storm drain can be comprised of closed conduit, open conduits, or some combination of the two, although usually it's open conduit. And these are particularly prevalent in urban areas, and designing them is especially challenging for a lot of reasons, not all of which are hydraulic. The actual design and build involves heavy traffic and risks associated with the construction. There's wide roadway sections with relatively flat grades, both longitudinal and transverse, so it's actually difficult to convince the water to go to your inlet. The flow is generally shallow. There's often no side ditches to help convey flow. And then eventually the flow is concentrated, preferably where your inlet is, but sometimes where it's not. There's a potential for costly property damage from water ponding or flow through built-up areas, which is the main reason for doing the design. And bear in mind that our roadway sections are intended to carry traffic, and they play a secondary role as channels to convey water. Usually in urban areas we have limited right-of-way, the outfalls are not conveniently located, the infrastructure itself impacts multiple jurisdictions, so we got a lot of people looking over our shoulder. And at some point in the near future, water quality is going to become more important with urban drainage than it is today, and it's already important. So for designing storm drains, we have a fairly simple process when listed as bullet items here. We establish the design parameters and criteria. We choose the layout, component location, and orientation using appropriate design tools. The key thing is comprehensive documentation, mostly to keep the lawyers satisfied when something goes wrong. And there's a fair amount of iteration in the process. So as you make the design, you realize a certain component isn't going to work satisfactorily, so you have to adjust that, which causes you to have to readjust most of the remaining part of the design. So there's quite a bit of iteration involved. In streets, there's curb and gutter sections, and this diagram here is depicting a curb and gutter. So this drawing here is taken out of a design manual. And here is the same cross-section kind of indicated by this greenish area right there. And here's the inlet. This is a combination grate and curb inlet. This is probably not in Texas. I don't think we'd use a precast cast iron insert. I could be wrong. But anyway, that's regardless of the point. And when the flow comes, it looks to me from the photograph like it's intended to come around this corner into the inlet and then from the frontal part of the picture towards the inlet. So the transverse slope or the cross slope is indicated by this blue arrow here, and it's the slope that's going that way. There's the curb. There's the gutter. And here's the cross section shown with these dotted white lines. There's longitudinal slope, so that's in the direction of flow. Transverse is perpendicular to the direction of flow. And those are all the defining concepts for curb and gutter. Ditch sections come in a variety of shapes. Here is looks to me a trapezoidal ditch. And triangular is common. Those are also called swales, either symmetrical or asymmetrical. Trapezoidal is pretty common. And segmental, I think they're trying to mean segments of a circle. I actually don't understand that word. But nonetheless, the cross-section depicted in the photograph is mostly trapezoidal. Maybe that's a triangle at the bottom. It's hard to tell. And there is the cross-sectional flow area when the ditch is full, and actually we have flow going above the ditch onto that motorway, and it's a trapezoidal ditch. So the flow and curb and gutter sections, there's several equations in the Texas Department of Transportation Design Manual and similar FHWA manuals, and they are used to determine things like flow depth as a function of computed discharge. And if you look at this carefully, it's not difficult to tell that this is a Manning's type equation. that's solving for depth of flow at the curb, which is where it's normally defined, in terms of discharge, which we be computed independently using hydrology. And the top width, ponded width, or spread width is also a manifestation of Manning's equation. So S sub x is the cross slope or transverse slope, and S is the symbol for longitudinal or slope in the direction of flow. So the rational equation is pretty much used on a vast majority of urban storm drain designs. We've seen it already, we'll see it again. Q is equal to CIA, and then you can adjust depending on units, whether using SI or US customary. And in the case of US customary, I, the rainfall intensity, is in units of inches per hour. Area is in units of acres, and that will produce a peak discharge in units of cubic feet per second. The intensity is the ratio of accumulated depth to averaging time. When we're dealing with inlets, it's also called the inlet time. The runoff coefficients are tabulated. You select from a land use description. This time of concentration applies to the surface part of the flow. And then later on, we're going to add an adjustment to it where we're going to account for travel times in the conduits. And that's how we can do a quasi-hydraulic drainage system design, which produces usually pretty good first estimates of what your design drainage system needs to be. So curbs are bounding features in a roadway. They vary in height from almost negligible to nearly 8 inches. They serve multiple purposes, redirection for errant vehicles, and they're a bounding feature for water running in the roadway as open channel, and they provide the constraint that allows them to become part of the inlets. The curbs are actually part of the structure that holds an inlet together. The primary design criterion for urban storm drains is the ponded width, and the goal is to keep at least one traffic lane open depending on where the actual design is occurring. So the ponded width increases as flow accumulates. So in this case, we have flow accumulating moving to the right in this diagram. Here's a slope break. And so it accumulates, and as flow accumulates, the ponded width gets wider and wider to carry that greater and greater flow. And it's accumulating from flow coming from the sides. As the average velocity of contribution increases, the travel time for a given distance decreases. And other things being equal, as the travel time decreases, the critical duration will decrease, and the intensity that one would compute goes up. So controlling velocity is very important to give the system time to actually respond. The ponded width usually involve all cross-slope values. So in this two-slope system, there's a steeper slope closer to the curb and a shallower slope closer to the crown. And the transverse slopes are considered collectively. The ponded depth is defined at the curb. If it's an inlet, the depth is measured from the lip of the inlet. And we place inlets at locations so that it will reduce the ponded width and keep the road passable. Good locations are obviously low points in the system. Intersections are desirable locations for two reasons. One, you want to keep the intersection free of ponding as much as possible to prevent a bad case of Dodge car going bad, and everything to control acceptable ponding width. So here is a diagram of an inlet that's controlling ponding width. Sometimes it's desirable or necessary to allow carryover. That's fine, you need design for it. And the locations are ultimately dictated by physical demands, hydraulics, and or both. Logical locations are sag locations. That's absolutely almost necessary. Near intersections, at gore islands, and at super elevation transitions. That's where the angle of the highway changes. Super elevation is like a banked curve, and then if the banking direction changes at the transition, there's a moment of zero slope. That's where you would want to try to locate inlets very close to that to capture the water that would otherwise collect in that zero slope area. The allowable ponded width guides the location selection. Now, for transportation infrastructure, typical guidelines are half width of the outer lane for main lanes of interstate controlled access, the outer lane for major highways, and in minor highways or in city streets, often limit ponding to width that allows one lane of traffic to pass. So some of the types of inlets in common use. One is a curb inlet on grade. So to design the curb inlet on grade, our goal is to determine this required inlet length, how long the opening is. These little extensions here. In this drawing, I mean the opening is the size of the vault box, but for longer openings, there's extensions off the vault box which are cantilevered, which is why the curb is so important, because it provides the structural rigidity when the vault box and the extensions are added into the design. Our goal, we would compute the length of inlet for total interception. Then we make a designer's decision of the actual length that's required. Sometimes the computed required length doesn't fit the physical constraints of the location, and so we would accept some carryover, estimate that carryover, and apply that to the next inlet location. These inlets come in 5, 10, 15, 20, and 25 foot opening lengths. I believe 25 is the biggest. The design guidance is discussed in the Hydraulic Design Manual, pages 1030 through 1035. Let me briefly exit the presentation and find those. Design Manual. There's a PDF version here, and there's also an online version. I'm going to gamble on that one, see what we come up with. So we're probably in the storm drain, which is chapter 10, and storm drain inlets. And here we have the curb opening, and now you can figure out where I actually got the picture. So in this diagram, it discusses the different kinds of inlets. And then as we move on down, discusses the location inlets, where to locate inlets, and then finally it goes into the various flow calculations. Now we're going to go through these in the PowerPoint shortly, but the point here is to show you where the locations are, where the information is located. Okay, so let's return to our deal. Okay, so in pages 1030 through 1035, which is the equations, what we need to know is the geometry, our desired capture flow, or the flow that we want to at least try to capture. We'll calculate something called an equivalent cross slope using some of the equations that I just showed you where they're located, and then ultimately apply a formula for the required inlet length. There's a brief discussion in the manual on the importance of carryover, or that it can use a little more of the open area of the inlet. That's probably true, but I don't think it's terribly useful. But that's beside the point. You can read that on your own. When we go through all the various equation calculations, we ultimately come to this one equation, 1015, and the point of it being shown here is that the required inlet length is directly proportional to the 3/10 power of the slope. And what that manifests itself is as the slope, the longitudinal slope is increased, made bigger, the inlet has to get longer for complete capture, and it's quite feasible that on a very steep portion of drainage that there are going to have to be multiple inlets spaced fairly frequently to be able to achieve complete control of the spread width. The next type of inlet is called a sag inlet, and sag refers to any inlet that's placed in the low point of a vertical curve. There's a lot of different actual geometries. This photograph is of a type H, basically a rectangular hole in the ground that has a vertical drop beneath it to connect into the storm sewer system. The key feature is that it's at the low point of a vertical curve. So as the vertical curve decreases, moving downhill to its low point, and then starts uphill, the spread width would be anticipated to start to get large in the sag condition, and that's where we're going to need an inlet to control that spread width, as well as to actually drain the puddle that's going to form when there is runoff. These are sometimes placed in medians, which are those trapezoidal ditches that are between two highways and a controlled access highway. And in cases where their slope is a little too steep, or there's a desire to get complete capture, a berm is placed downstream of the inlet to force ponding upstream, to force water into the hole. When that's done, it might look like this in plan view, and so it doesn't seem like the spread width, in this case spread width isn't on the highway, it's in the median. Doesn't seem like there's much impact on the spread width, but what's more important is there's no additional flow downstream, there's no carryover. There's a series of movies that are available if you want to watch them, and these are some physical experiments of these drop inlets in some different conditions. So one is with a grate on grade, and if you look at the edge here, it's difficult, but there's a little bit of impact on spread width, but it's not as great as we'd want, and certainly not complete capture in this picture. Go ahead and institute a ditch block, and there's some fairly turbulent flow just downstream of the hole in the ground, but all the water's captured, and you'll notice how the water spreads, and then there's reverse flows. There's also tandem inlets in the same configurations on grade. They don't appear to have much impact on the spread width, although they're capturing water. And again, if we block their downstream side and force ponding, even though the spreading here is wide because we're forcing a pond, we get complete capture. So it's all going to be situational dependent. The design discharge is based on the hydrology using the required annual exceedance probability, the surface area that drains the inlet, and the time of the concentration. Basically table 4, I think, in the design manual. Let's see if I can remember what it is. I think it's table 4.2. Table 4.1. Okay, I lied. Table 4.2. So it has recommended design exceedance probabilities for various facilities. The ones that are in the bracketed X's, I believe, are the brackets are recommended, and then federal directives override many of these things. So, so inlets and drain pipes are designed for 5-year or 10-year AEP. Usually we don't worry about the larger ones. Storm drain systems on interstate highways, the inlets are designed for 10-year annual recurrence interval and 50-year annual occurrence interval for depressed. Okay, so this table, as you're aware of where it is, and so we'll continue. Once we know the exceedance probability, we can apply the hydrology methods and calculate a time of concentration, also called the inlet time, to that inlet. And then the steps for the inlet are as follows. State the desired risk, determine the area that will drain to the inlet, determine an appropriate inlet time or time of concentration. If the number is less than 10 minutes, then the guidance is to use 10 minutes as the averaging time. Compute the intensity from that time of concentration. These tools, EBD lookup or the equation of hydraulic design manual, you can consider them obsolete, and you'd want to use the NOAA Atlas 14 Volume 11, at least for Texas, and then the appropriate volumes for the other part of the country for the locale where you're doing the design. Estimate a reasonable runoff coefficient, so that'll depend on whether or not all the runoff is coming from your paved area or if there's a combination of paved and unpaved area. Apply the rational equation to estimate the design discharge, and that's what we're going to try to capture with an inlet. Based on that design flow, gutter geometry, and longitudinal cross-section, then we apply one of the various sets of formulas. Let's quickly go in the manual and see what those look like. And I just want to call your attention to all the different equations. So this is for curb on grade, and there's a series of calculations that you make, and I'm scrolling through them quickly. You can read these on your own, and your goal is to get to the required inlet length. If you can't capture it all, then there's biplast, which is carried forward to the next inlet. If you're in sag configuration, you determine if the flow depth is below or above the height of the inlet opening. If it's 1.4 times or less than the height, you're going to use this Weir type equation. If it's bigger than that, you use ORIFICE. If there's going to be variable flows, you will ultimately use both. And then select an inlet length that's equal to or greater than the required length. That's a standard inlet length, meaning it's going to be an increment of 5 feet. For slotted drain inlets, there's a similar design procedure, a little bit more elaborate equation. And for trench inlet, another elaborate equation. So all these you can figure out by reading. So we start with curb opening inlet design variables, the ponding width, the gutter depression width, and the inlet height. And then we apply equations 10.8 through 10.16, although not necessarily in that numerical order. And start with 10.1 to get the depth at the curb. Use 10.2 to get the spread width. Use 10.8 to get the ratio of the conveyances. Use equation 10.9 to compute the actual conveyances for each different part. You have the area of depressed gutter section, wetted perimeter depressed section, area beyond depression, wetted perimeter beyond depression, and these are all combined to come up with an equivalent cross slope, and the equivalent cross slope times the longitudinal slope in this formula is what calculates the required inlet length. So there's one online tool that's applies those equations in the sequence to come up with required length. So if so value for inlet, let's say our computed discharge is 12 cubic feet a second. We have a cross slope of 0.02, which is 2%. Longitudinal slope, make it pretty flat, 0.5%. Manning's roughness, value for depressed section width, I don't make it 2 feet, make a big one. Depressed section depth, 0.0253 inches. Yeah, what the heck. 1/4 of a foot. And all this does is implement that series of equations that are described in the design manual to come up with a required length of 24 feet and some fractional component. And there are 25-foot inlets available, so you could specify a 25-foot inlet to achieve complete capture. If, on the other hand, you don't get complete capture, then you have to figure out what the carryover would be. So let's suppose we specified a 20-foot inlet. My guess is maybe, so 11 CFS is 22. But here's the beauty of having it all coded up. 10 CFS is 21. Close enough. So at 9 cubic feet per second, a 20-foot inlet will almost get complete capture. Let's go real accurately. How about 8.5? That's good enough. So 8.5 CFS is completely captured by a 20-foot inlet, and we have 3.5, we have 3.5 CFS that carries over. So our next inlet's going to have to be including that 3.5 cubic feet per second that was carryover. There's also a spreadsheet tool. It simply works the same way as the tool I just described online, although you can pre-supply carryover ahead of time. Let's actually use these numbers, see if we get the same number. Depression depth is 0.35, depression width is 5. It's easy enough to do that. Okay, so our discharge is 11. Our cross slope is 0.02. Our longitudinal slope is 0.035. Manning's N is 0.13. Value for depressed section width, 5. Depressed section depth, 0.35. And it calculates a 19.92. Same, should be the same. It's using the same equations. When we're in sag conditions, then we have to check that what the curd depth is relative to the opening height. If the depth is greater than 1.4, we use orifice conditions. If it's less than 1.4, we use weir flow conditions. Here's the orifice equation. You look up the value of C0 in the design manual, and D0 is the flow depth, H is the height of the opening, L is the width, the required width of the opening to capture the value Q. For the weir equation, length is Q divided by the weir coefficient times d to the 1.5 power minus 1.8 W, where W is the width of the opening. Here's standards for drop inlets. There's no importance that you can that you be able to read these. The point is there are fairly elaborate holes in the ground. There are vault boxes that connect to pipes. It has some specifications on the grading system to make it traffic safe so that wheels don't fall in. And then for an inlet like that, it's placed in a sag condition, and the lower of the curb height and depth associated with allowable pond width is what we designed for. We determine the capacity as a weir. In the case as a weir, the perimeter controls the capacity. Then we can turn the capacity as an orifice. In that case, the total open area controls the capacity. And we can plot the two as a horizontal axis of head, or think of it as depth. The vertical axis is capacity. And so when there's not very much depth, it's weir controlled up to about 1.4 times the height, and then it's orifice controlled. And so it would follow this red curve. The main point is once it goes into orifice control, to increase the capture flow rate, you actually have a fairly substantial increase in head. So orifice control is generally the opening controls everything and the head doesn't play much of a role. There's also spreadsheet tools for that. I don't have an online tool, but this implements the various equations in the hydraulic design manual. They're listed here. It's online. And next time we're going to discuss the rational method for storm sewer conduit sizing. I call it a by hand method. We'll be using Excel to handle the arithmetic, but it is literally by hand. And don't be too deceived by the Excel spreadsheet. It makes it look like it's automatable, but there's a lot of designer interaction to work through these spreadsheets. And these are used to obtain initial estimates of required diameter flow lines, slopes, and the hydraulic grade lines. And then I stipulate that once the initial estimates are done by this rational method, they should be placed into a hydraulic model such as SWIM and tested in that model to be sure that the hydraulics are indeed preserved with what you expect. And we'll discuss that as over the next few lessons. Thank you for your attention. Have a good evening.